Before we start with the unsupervised topics, a bit of logistics. So we had a couple of people who were struggling with AWS. So first of all, don't panic. The homework is set up in a way that you should be able to solve everything on your local machine. So you do not need to go through AWS to solve the homework, submit, and get full points. That being said, it's an extremely cool tool in your toolbox to have, also for the final project. So we would like for you to have an experience with AWS, which is why we set all of this up. So turns out the lab actually gave you instructions for Spark 1.3. Rahul now did an update for Spark 1.5. This is a post on Piazza. So if you're running into problems with the old version, please check these instructions out. And then we had a few cases who actually were charged. So first of all, when you registered for AWS Educate, you did not automatically get this credit of $100. Or it should be 100 if you correctly identify with Harvard University. What you do get is a confirmation email. And that email includes a code. And this code you have to redeem in order to get your credits. So even if you don't use AWS for this homework, but want to use it for your final project, or actually these $100 are not tied to the course. And I believe they're renewed each year. So these are completely for you also to play around. So register, it doesn't hurt, it doesn't cost you anything. But please sure to redeem that code, because otherwise it's your credit card that gets charged. And then we had a couple of cases who actually didn't notice that an instance was still running. And people went through the lab notebook half through, and I'm a bit concerned about the homework. Like you start working on the homework and you have the cluster open, and you just decide to start to go on another day, right? And you leave that cluster open. That's going to generate charges. So be sure to shut down your instances. And what happened to people was they tried to make sure they shut down their instances and did everything correctly. But unfortunately, there's this region setting in the upper right corner. And if that region is set to something else than the East Coast, then you might not see your instances. I have a screenshot here from my AWS console. You can see up here is the US East setting. So you need to make sure, if you use the lab notebook, that you have the right region setting there. Otherwise, I think the default was something in the West, California or something. And if you actually have your setting wrong, you won't see that instance running. So people have been charged up to $70 before they found this. So please try to check. And if you incur charges, write me an email. So this setting here, please check, extremely important. And make sure that your instances are shut down. The way also to sanity and double check that you are in the right region, if you've used a cluster, also clusters closed should be listed, right? So if you have a completely blank slate and you have used AWS before, that's an alarm signal that you're in the wrong setting there. So, but also more details are on Piazza. I just wanted to highlight these posts because sometimes they get buried and it's your money then at some point. So more announcement about the final projects. We've done all the team assignments. So the majority of the course, the vast majority, should have teams. Either you came up with groupings on your own, or we did a random assignment. If you do not have a 3 to 4 person project team yet, you are starting to be in trouble because the proposals are due on Thursday. So really try. We have this dating idea within the Piazza thread, like people are trying to find groups. And if you're in serious trouble finding someone, please write an email to staff@cs109.org. And we're going to come up with a team for you. So, and as I already said, the proposals are due on Thursday. You can already submit the proposals. The form is linked on Piazza. The idea is your final project needs to be approved by a TF. And in the following week is the project review week, which is the week we dedicated for you to meet with the TF. If you registered early, you might have already spoken to a TF, so you get more time to actually work on your final project. The idea is for you to get feedback. Often, projects actually are too ambitious. Already had 2 teams coming to my office hour, and I had to say, I don't think that's feasible to do in the time frame you have. Right? Because people get these really cool ideas, and there's really cool stuff that you can do with data science, but we have this restricted time frame, so you need something that you can accomplish within this time. Very important to also specify if you already have your data. Spending your final project time by labeling and making annotations in order to train some supervised classifier is not a good use of your time. Right? We cannot give you credits for having sit down and labeled 10,000 images. So try to look at your data sources and what you have. Then when you submit your final project proposal, it's just 1 form per team. So please don't submit each team member 1. We only need 1 submission per team. And I already said do it as early as possible. And here's a link again to the Piazza thread where you can find the Google form. So that was all from me regarding the final project and AWS. Questions? No, cool. Then let's go on with unsupervised learning methods. So far in this course, we've mainly dealt with supervised methods. What do I mean by that? Remember, we always had our data matrix X. So we had our data always came in Y and X, right? And X was this large matrix where you had 1 sample per row often, and then here you had your different features, right? And then Y would be some form of class label. So for our handwritten digit recognition, for example, each of the features was one of the pixels in a patch. Each row in this matrix was one particular patch showing 1 digit. And then Y was the class, right? 0, 1, 1, 2, 3 was giving you the actual class of that sample. So in a sense, there was this teacher present who told you this sample is meant to belong into this class. And that's what we mean when we talk about supervised. And now for the rest of this lecture, I'm going to talk about methods which do not use Y. So we're going to look at the problem where we only have 1 big matrix X, and we're missing this label information. And there are some applications in clustering where the problem actually would need a Y, the problem you're trying to address, but it's somehow too expensive to generate that Y. For example, in the beginning, people were too lazy to label images, and they approached image segmentation as a clustering problem, which means they tried to avoid having people sit down and mark all the neurons in an image, all the cancer cells. They were trying, because a human can look at this, right, and see these are cancerous and these are not. So they were hoping that these structures would just somehow pop out of the patterns. And then over time, supervised methods just worked so much better that people realized it's worth putting in the effort of having someone label. And if you think about it, the human also learned like this. Humans in the beginning often have a teacher who says, well, this is a cancer cell and this is a not cancer cell. So what happens if you don't have that teacher? And Joe actually already talked to you about unsupervised learning. LDA is an example. Nobody told you which topics are in these documents, right? You just have this collection of topics, and you say, here go the collection of documents, and you say, here go black box algorithm, give me the topics, right? And then it came up with these clusters that then were named, right? That it's dealing about genetics or computers in these different articles in the slide Joe had. So, but the important part is we do not have labels in our data. So what does that look like? We always had these scatter plots. And most of the scatter plots I showed would have more colors in them, right? So normally these guys would be red and these guys would be blue. And this red and blue encoding was actually the value for the Y. Now we're in the situation where we don't have the y. So all we have are the points. And the task becomes much more difficult now because we cannot use the y to guide us to somehow find a separating hyperplane. Instead, we have still this notion that there is a pattern in this data. For example, here, I could say, well, there somehow is a cluster here, right? And there is a cluster here. So if you would tell me in advance where there actually are two different classes here, orange and apples, cancer and non-cancer cells, right? Measurements from females or males, I would say, well, most probably these are all belonging to one class, and these are all belonging to the other class. Why? Just because of this notion of distance, right? All these points are somehow near, clustered together, and here I have another cluster of points. So this is the idea of unsupervised learning, to find patterns in this data. And sometimes the problem is in a way that you already know which patterns you're looking for, but it can also be used to maybe find new patterns. And that's also more the data mining direction. That's also a very interesting topic also in sciences. Like biologists who gather a lot of data and then come to you and say, can you find something interesting? So here are a few applications to show you what clustering is used for. Google image search. I don't know if you paid attention to this, but if you go to Google and you look for a tiger. And now I'm going to the images. Do you see this at the top? Like a few years ago, I would actually only get this list of images, right? Just this tiling. But now you see it came up with categories up here. Baby tigers, white tigers, faces, drawings. And this can be done in an unsupervised manner. So you have all those image patches, and you try to find which of those could belong to one class, without someone actually telling you, well, there are baby tigers and white tigers. You don't know the clusters in advance, right? It depends on what people uploaded. So it's hard to define before that it would be useful to have a cluster of baby tigers. So another fun thing that I found is Microsoft has this visualization of citations for papers. Here we see Hans-Peter. So there is a cluster shown with Hans-Peter in the middle. It's his cluster, and here are all the different co-authors he had. So there's a notion of similarity, of distance, and here the distance is how many papers were authored together. And then, of course, because this is about Hans-Peter, it's the one in the middle. So that's his cluster. And I just want to show this because I thought this is really cool. There's also this notion of a co-author path. And do you guys know what an Erdős number is? So this is just for fun. No, this is not really a clustering problem. It's a path-finding problem, right? So Erdős is this Hungarian genius mathematician who had a very eccentric lifestyle. He would ring at people's doors, crush on their couch, and in exchange write papers with them. So he would go to a brilliant mathematician and say, let's write a paper together, and I live at your place. And then he moved on. And I'm showing this because I have to show off our Joe. So he has an Erdős number of 2. And that's a real accomplishment because the numbers, the lower they are, the more brilliant the mathematician uses to be. Because Erdős was selective, right, whom he would publish with. So this guy knew him, and Joe knows this guy. Okay, so that's a clustering application. Also, one more structural one is this concept of Delaunay triangulation. So let's say you have a map and you want to find a new location for a hospital or police station. You want to optimize it. Then you also have this notion of police stations that already are somewhere, and you need to find where to put the new cluster, and the cluster is basically the region around it that this station serves. And you need to optimize the new placement for the police station. And you might have weights, right, on areas that have a very high crime rate, versus others that are very safe. And there's also outlier detection. You can do outlier detection with clustering. It's this notion of finding patterns. And once you identify a pattern, then you can also say, well, this point actually does not really fit into the pattern I found so far. And my favorite outlier detection, I actually don't know what exactly they're doing, but CERN has this very, very big outlier detection problem, right? I was there years ago, but they told me they actually generate too much data. They can't keep up with it. So what they have to do is they throw nearly everything away and only keep the outliers, because those are the interesting events. So you could try identify patterns. This is also a case where they actually don't know what all might come up in all the data they record. So you're interested in the points that do not fit the pattern. But for that, you have to identify a pattern that you actually don't know in advance. So clustering. So the methods we're going to talk about today in specific are k-means, mean shift, and hierarchical clustering. And then because we don't have our Y labels, it's actually also not straightforward how to think about evaluating a clustering. Is it a good solution? So we're going to talk also a bit about that. So k-means, popular first choice clustering algorithm. You initialize k random positions. That's now where the k comes from. Before we had k and n, there was k nearest neighbors, not to be confused with k means. But k, again, is just a number that we have to predefine. So here k is a number of random positions that we assign in the beginning. And then we assign cluster centers to these positions. That sounds a bit abstract. All that it means is I take my data points, I sample 2 completely random positions, put those points there, and say this is now the center of a cluster, which in this very first initial step doesn't make sense at all, because I said I want one cluster here, so I would expect a cluster center to be somewhere in here, and I want a cluster here, so a cluster center should be somewhere in here. But we initialized this algorithm just by choosing 2 arbitrary centers. Now we proceed, and we say, we compute the distances of all the data points we have to these cluster centers, and assign the points to the nearest cluster center, and then update the centers as the mean of those. So, and that looks like this. I have my 2 initial random positions. Now, for each of these points, I calculate the distance to the 2 centers. And then I look which one is it closest to, and I assign them. So this gives me some form of decision boundary. And the decision here is which cluster center should the point belong to. So these are all the points that are closest to this guy, and these are all the points that are closest to the blue guy. And now comes the update step. Now I update my centers to be in the middle of the points it was assigned to. So here I have kind of a center of mass, so my point goes towards this direction. And here the blue guy was a bit more undecided, but these had the stronger pull, so it goes more towards that direction. You can already see it's converging to the 2 cluster centers, because now we do the whole thing again, right? We compute all the distances of the points to the 2 centers. And now if we do the next assignment, we already have this notion of these 2 clusters that we intuitively know we were looking for. And we update this again and again, and you can see it iterates slowly to the centers of these 2 clusters. So that's the idea behind k-means. And you can do this with more cluster centers, like you're not restricted to 2. And this is actually a video that shows you how the points come in, all of them, and how the algorithm then with the updates converges to these different cluster centers. And you can already see the clusters is looking for are kind of blob-shaped. That is this notion of similarity that we have, right? Just Euclidean. And this is an example which I believe was actually done with k-means for color compression of images. I actually don't know whether people do this still nowadays, but in the old days of the internet, you actually had to worry about your GIF files and how many colors you used in them. So you would use an indexed color palette, and you would have to optimize the number of colors. The other option where you could use this is to actually try to do image segmentation unsupervised. So I have this super interesting image here with bell peppers. And what I'm going to do now is different from what I did in the past. And I think this is actually a source of confusion for the slide. So in the past, I had an image patch, right? And I said all the single features in my X matrix are all the single pixels in there. Now the problem is different. Now each pixel in this image is one data point. So for each pixel, I get one row in my X matrix. And I only have 3 features. And these 3 features are the color channels, red, green, and blue. So the way this image is saved is for each pixel, I have 3 values, which you see here come as color. So here I plotted the 3 different color channels, and you can see these yellow guys here, for example. Bright means has a higher value. So you can see the red pepper, of course, has a lot of red, and not much green, and not much blue. And the yellow peppers, for example, have a lot of red and a lot of green, but no blue. Can you see that? So each pixel now is in a 3-dimensional coordinate system. And what I'm doing now is I'm clustering on these colors. So I can say I only want 2 clusters, and I get this. And what I did here is all the points that were assigned, all the pixels that were assigned to this blue-greenish cluster, I colored in the color of the cluster center. Does that make sense? If you have a coordinate system, right, and let's say this is somehow a red channel and this is somehow a green channel. And I'm skipping the blue channel now because I suck at drawing 3D stuff. So all the yellow pixels would kind of end up here, right? And all the red pixels would have a lot of red in them. And all the green pixels would have a lot of green in them. So if I assign now, let's do 3 clusters because I did 3 colors, and I get somehow this notion of a cluster center here. So let's say here's the center for the green cluster, for the yellow cluster, and for the red cluster. What I did now is all of the pixels that are closest to the red cluster, I colored in red. And all pixels that are closest to the yellow cluster would be colored in yellow. So these pixels are a bit spread out because they don't all have the same red color. I'm making them now, I'm forcing them to all have the same red color, which corresponds to the red that is given by this center of the cluster. That make sense? So here I only did 2 clusters, and now let's do 3. So 3 kind of give me this blue sieve around here, and I could even claim that I kind of segmented the green pepper out. So it does work a bit. Image segmentation supervised works better, but this image has, I believe, 256 colors. And I can increase the number of clusters here. And I think these are 10. So with 10 colors, I'm already kind of close, but we have this notion that maybe already with like 50 clusters, I would have a representation that is pretty faithful to the original image, and I just reduced drastically the bits I need to represent this image. So I mainly did this because it's a nice visualization of the problem that K-means has, which is this. These 2 images use the exact same K. I believe it's 10. And what you see is they're different. So why do you think they're different? Yes? Yes, that's our problem. We initialized randomly in the beginning. All the other stuff is deterministic, but we initialized with a random position for our cluster centers. The method is guaranteed to converge, but not guaranteed to converge to the same solution. And as you can see, it actually will converge to different solutions. And then it's hard to determine which one should I choose, which pattern is the one I actually was looking for. So As I said, it's guaranteed to converge, but the result depends on the initialization. And the number of clusters is important for the solution. And a drawback of the method is actually you have to specify the number of clusters. And sometimes you know that number, and it's very easy. Like if you know you want to classify cancer and healthy cells, you already know you're looking for 2 classes, right? But if you're working at CERN, it's not immediately obvious what your K should be. And it can be sensitive to outliers, these results you get, and you can kind of mediate that by using the median instead of the mean for your updates from the centers. So these are things you can do to address these issues, but they still remain. So you can also play around with the initialization. So we set random positions. You can also choose random data points, right? So instead of going completely into the feature space and picking 2 positions, I'm basically saying, well, the points kind of have to belong to a cluster, so it makes sense to pick random data points as my initial cluster centers. You can also do random cluster assignment to data points first, and then do this update step and look where the centers end up with. And you can start several times. The notion is, with clustering, there's this idea of stability that we're going to talk about later. And an idea is if I do k equals 10 and I do 100 runs of the clustering and with different random initializations, and I get one solution 90 times and another solution only 10 times, then I would prefer the solution that came up 90 times, because it seems to be more strongly in that structure that we're looking for. So how do you find k? Think about the extreme cases. If k equals 1, I have all my points in one big cluster. So I think I'm going to draw that. So if k equals 1, I'm only getting one cluster center, right? And it means all these points get assigned to the same center. And what we can see is this one center point actually doesn't explain the structure very well. Now, if I choose 3, and I end up with this solution, I can visually see that the pattern in the data is very well explained. What if I choose k equals 5? Remember that k is fixed. The algorithm has no other chance as to come up with 5 cluster centers. So what's it going to do is, it's going to pick one center in the middle, and then it's going to split the other 2 into 2 clusters. If I force it to find 5 centers. And there's this bit notion that goes in the direction of overfitting. I'm explaining too much of the variance in the data here. So, and there is a way to visually explore this idea that is called knee or elbow method. This is visual, and it depends a bit on your intuition. It actually depends mostly completely on your intuition, and it might be not as obvious as here. But sometimes you can like plot this and say, well, here's my k. This is what I'm going to use. So what is plotted here is, this is k. This is the number of clusters used. And this is the within group sum of squares. So the sum of squares here is meant, what is the distance from all the points to their closest center? And if I only have one center point, then this distance is very large. If I come up with the 3 perfect clusters, this distance is significantly reduced. If I increase it to 5, it doesn't reduce the distance anymore that much. And this is the idea. Like in the beginning, so this is the data, and there was just one cluster, right? So they actually did this for k equals 1, k equals 2, k equals 3. You have to do this in order to get this graph. And for that, you plot this within group sum of squares. And you can see in the beginning, it drops a lot. This is when you explain a lot of the variance in the data. And then there comes this knee or elbow in the graph, where your points don't help that much anymore. And this is where you want to choose your k. So k equals 3, because afterwards the k's didn't help that much anymore. That's the idea behind this method. And then it depends on your application. If you were just looking for a pattern in your data, you can just do this directly on all the data you have. But if you have this notion of afterwards, I want to have unsupervised data coming in, new data coming in, I want to generalize to new data, then no surprise, we're doing cross-validation again. So instead of using the same data to compute this width and sum of squares, you would have one training data that you use to solve your k-means, and then you have the validation data coming in, where you compute all the distances to the groups that you just identified. So it's the same idea. And this is our basic cross-validation scheme that we by now all know by heart. So that's the idea behind k-means. That was our first clustering method. Questions about k-means? Yes? So I didn't completely get. Do you know how? Are you asking how to identify the knee, or are you asking why we're not using that k? So I think the question is, why would you go for this knee instead of using the larger k? Because as we see, it explains the in-class variance more, right? So your sum here of the distances went still down with the higher k. And the reason is here. So this 5k here, if I would have given this graph, this plot to you, and not told you how many clusters you have in here, I think without doubt, anybody of us would have said 3, right? Because you have this notion of 3 clusters, right? Now, if I do 5, the distances here still get smaller, right? If I increase k, the distance, I mean, think about, again, about the extreme, right? If I choose k equal to the number of points I have, then each point ends up being its own cluster. And your sum of difference there is 0, right? So that would be your optimal solution if you just minimize this variance. It's like with the k-nearest neighbors. The principle is the same. So what instead you're trying to find is this trade-off, again, between the flexibility in your clustering and how much it explains. So this is why we're looking for this knee-elbow structure. Is that the same question or a different one? Yeah? Yes? So the question is, why would you not want to validate? The reason just is that you have less data to actually do the clustering. And sometimes you're just looking, for example, I had this notion of trying to find the new police station. This is a problem you solve once, right? And there is no new data coming in where you would want to generalize the clusters you found. So in this scenario, I wouldn't bother that much about choosing k in a way that it generalizes, because I'm actually interested in solving this particular problem. So the question is, wouldn't use cross-validation give you more confidence in your final solution? I say yes and no. The notion is this confidence. What do you want to be confident about? And the confidence that cross-validation gives you is confidence into generalization. What cross-validation gives you a good notion that your solution will generalize to data that you have not seen yet. So the question is that your purpose? Is that what you want to get out of your clustering in the first place? And yes, it might be. There are several applications in biology and things where people say, well, here's one data set, find a pattern, and then you want to find the same patterns in the next data set. So in that case, then, I want to be confident that it generalizes well to the next unseen data. But you have other applications where generalization is actually not the goal. The goal is to find a pattern in this data, right? And then I wouldn't bother cross-validating. So the idea is, what do you want to be confident in? Okay. Yes? Oh, that's a very good question. The question is, how do you check that you converged? What you typically do is you check how much your cluster centers moved, and then you specify an epsilon. You say if it's moving less than epsilon, then I'm done. A very good question. Okay, no more questions? Then let's get rid of K, because having to specify that K is pretty annoying. So we've seen we can try this elbow-knee method. I'm going to show you a different method in the end where you can look for the stability of a clustering. But still, it's annoying. If you don't have a problem where K is obvious, you would most probably like to avoid having to specify it. And we can do without that K. And this other method is called mean shift clustering. Mean shift clustering is conceptually very simple. Computationally, it's very hard, just in the sense it needs a lot of computations because you need to determine a cluster for each point. But I'm getting ahead. So what is mean shift clustering? The idea is for each point in your data set, you specify a window around that point. And that window has the same size for all the points. And you look, so now this point, basically it's a cluster center, and you look for all the points that are in a specific distance to that point inside this window. And then you compute the means of all the points in that frame, and you shift the window to this mean. And then you repeat this until convergence. And this video is so much simpler than me trying to describe this. So what you see here, this is a window around a point, and it gets updated, right? So here's the mean of all the points inside, and I shift over. You again compute the mean of all these guys. So this window is drawn to the mass here. So the points are much denser here, so each update you get is dragging the center of your window towards this cluster of points. That's the whole idea behind mean shift. It's that simple. And so there's the notion here. You have to do that for every single data point. So for each of these data points, you start and you put the window around and you shift, shift, shift. And what you're going to see is, if you have points distributed like this, all these points, when you update, because there's gradient, right? There's this gradient of density of points here. And the window is always going to shift towards the denser region. So the notion is that all these points are going to end up with the same center in the end. And that center is your cluster. So here's an illustration for different window sizes. So here are single data points. And for each of these data points, there's been done this window method and shift, 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 shift. And what you can see in this illustration, this visualization, is the path that this window center took in each iteration. Those are the black paths here. You can see all these points here converged along these lines and then met in the middle. All these points here, like, traversed to the middle of this cluster. So we do not specify the number of clusters here. Instead, we have to specify that window size. And then we basically let each point be its own cluster center in the beginning, and we see where it shifts to. And then all the points that shifted to the same place are assumed to belong to the same cluster. And I said we don't have to know the number of clusters in advance, but what you can see already with this visualization is that actually the size of the window has a lot to do with the number of clusters that are being found. So you can see here the window was fairly small, sigma 0.6, and you end up, each color here is its own cluster. So you get a high fragmentation here of all your points. And here the other extreme case where this window was fairly large, because if you have this large window, it's going to smooth over little gaps, right? Little gaps in your point distribution, big window, they're just going to be smoothed out. So the window keeps shifting, shifting, shifting. You can see all these points now even shifted across. There's the spiral pattern here, right? A lot of clustering papers like to try these spiral patterns because they're really hard to cluster. And you can see because the window was so large, the points even traversed across the gap in the spiral to the same cluster here. So instead of finding the spiral pattern, it smoothed over this big gap and got these 3 blobs. So we don't have to specify K. We still have to specify the window size. It was not a completely free lunch, as always. But it has the notion of number of clusters here is more loosely than for K-means. So mean shift does not need to know the number of clusters in advance, and it can handle arbitrary shaped clusters. That's something very nice. It doesn't have to be. It depends a bit on also how you define the distance metrics. But so if the window was very large, it also ended up with these blobs. Actually, these are blobs as well. Huh, I didn't check that. I thought the whole point of the paper was to show that it gets the spirals out. Normally they don't get the spirals out for one window setting. Maybe they introduced a different metric here. It's robust to initialization. So we got rid, at least, of that problem, right? We said there's this randomness in K-means where you do the random initialization. You might want to run it just multiple times. So with mean shift, that is gone. With mean shift clustering, it's deterministic. As once you have the same parameter setting for the window size, it's going to give you the same solution. But you need to specify this window size, and it's computational, very expensive. Why? Because you have to do it for every single data point. You have to do this whole trajectory, right? K-means was more efficient. You just chose your 2 cluster centers, and for each data point, you only had to determine the distance to that cluster center, which is fairly fast. Having to compute this mean over all the points in the window, shift, compute the mean, shift, compute the mean, that's a bit expensive to compute. But it is embarrassingly parallel, so if you've taken CS205, shouldn't be much of a problem. So, and I linked here, I think this is a very, very good introduction to mean shift clustering, if you want to read more about it. It's one of the best explanations I found. And this is an application I found where they use this for traffic analysis. So they want to group motion trajectories. And the idea is this outlier detection idea. Identify people who do unusual things in traffic, because most probably they're violating rules or even risking their lives. So this guy is running across the highway, which is in general not a good idea. So what they did now is they looked at the object trajectories. And you have all these cars driving along the roads. And now they group these trajectories. So you can see there are these going here, and then there's the other lane here. And you can see the outliers here come up as their own cluster, because they don't really belong to these 2. So then you can catch the guy on the video that ran across the street. Same idea here. 2 roads, and then the outliers come up. You can see even here, like the pinkish ones were kind of their own cluster, and then there were the red ones on top of that. Let me try. That was too fast. Because this actually has 4 clusters, I believe. You can see this here. Like this one. Okay. There was one street going like this, right? One street going like that, and then you had only very few that took this kind of S-shaped route. But you could see that there were only 3 or 4 trajectories on top that were red. And these are then maybe traffic rule violations. So the idea is to automatically evaluate camera recordings. So, but again, there was no free lunch parameters. For k-means, we need our k. For mean shift, we need our window size. So the last method we want to talk about is hierarchical clustering. And that actually needs neither window size nor the k, because it just keeps a history of all possible cluster assignments. I'm going to show you how it does that. Well, first of all, application. So hierarchical clustering has this notion of you have all your data, and this is the tree of life. So these are organisms and how similar they are in terms of evolvement. And I believe there's a genetic component to this, and I think also similarity, some other measure. So things are grouped together, and you see this tree-type structure here that groups things together. So on a very low level, on the lowest level, actually, every organism is its own cluster. And then you can see that these groupings start to form larger and larger clusters of points. And these have meanings. So here are all the plants kind of in one cluster, and fungi here have another cluster. So this I would say is about this region maybe. So this is this cluster up here. So if it doesn't make sense to you, I hope it's going to come now. So this is a hierarchical clustering example now, extremely simplified. So I have my points here, and just for better visualization, I took very few ones, and I have lined them up here, and they're color-coded. So when you first start, every point is its own cluster. So it's really k equals n. Each point is its own cluster, and I have all the different clusters here. And now let's do similarity just by shortest distance. So I look at the 2 points that have the shortest distance, and yes, that means I need to compute the distance from all the points to all the points. And these 2 points here are closest together. So what I do now is I only group these 2 points together, and I mark them here in my dendrogram. So now these are in the same cluster, and I just chose one of the colors to show that they're in the same cluster. Now you're looking at the next pair of points. And these 2 here are closer together than these 2 here, so they are chosen next. And so we group these 2 together. And now these 2 here are the next ones that are closest together, so they get grouped. And now things are getting more interesting. So now this point here is kind of close to this cluster. So what happens is it gets assigned to these other 2. So I'm growing clusters now bigger, larger and larger. And then these 4 here get grouped together, and these get grouped together, and these. So I'm actually doing the whole solution. I'm doing all the clusterings from each point is its own cluster. To the other extreme, I only have one cluster. That is hierarchical clustering. And the trick is, then I ask the user. That is, for example, something you can do, because now I need to choose the threshold. Right? I need to choose a threshold where to cut off, and then the coloring that corresponds to. Why didn't I color those right? So this threshold here, for example, now says I do all the groupings that were done before this threshold, which means yellow, blue, green, and red belong to one cluster. No. Yellow and blue belong to one cluster, green and red belong to one cluster, these 3 belong to one cluster, and the purple one gets its own. And that is kind of an intuitive solution here that I picked. So these 2 go together, these 2 go together, these 3 go together, and this one stays alone. So that's the idea behind hierarchical clustering. I have one application later on where they use this for video segmentation, and often this makes sense because sometimes you have a problem that can be very fast done by visual inspection, and then you can just give the user a slider and ask, right? And this can be done very efficiently because in the hierarchical clustering you actually had the whole solution. So it produces the complete structure, and there also might be just benefit in that, as in the tree of life, right? We actually don't want to have a threshold. The idea is to see the structure of the data, and then biologists could see, well, this actually is one subgroup of bacteria, and this is one subgroup of fungi, you know? So they actually wanted that structure and how it belonged together. I think physicists do also something with galaxies, where they use dendrograms. Astrophysicists. So the hierarchical clustering idea is to produce the complete structure, and that also means you don't have a predefined number of clusters because you do them all. Now, this similarity there, that is something you might want to tinker with. What I did here was single linkage. I just looked at the point that was closest. I looked at the minimal min distance. So you have to have this notion of what does it mean? How do you determine which point should be grouped next? And that influences your clustering. So in single linkage, you look at the minimum. And actually, let's skip the formulas because I have this visualized. So single linkage looks at the minimum of the distance to the cluster. So here we say these guys here would be closest together. So if these are already in one cluster and these all are in one cluster, I go through every possible point pair between the clusters, compute the distance, and the minimum of those is the distance between these two clusters. So basically the 2 points that are closest to each other here determine the whole distance between this cluster and this cluster. And also between this cluster and this cluster, I do the same thing. So I get one number between green and yellow, and one number between yellow and purple, and one number between purple and green. And then I look which of these three numbers is the smallest. And that is the next grouping I do. So in this example, I'm claiming that this is the shortest distance. I did not measure that. So I'm grouping those. Now, complete linkage is kind of the opposite idea. I'm looking for each cluster, what is the maximum distance between points in this cluster. So let's say this is the maximum distance between a yellow and a purple guy. And this is the maximum distance between a green and a yellow guy. And then I'm choosing the smallest of this maximum distance. That is not that intuitive, but it gives you a different clustering solution that you might prefer. Because single linkage has this tendency to form very long chains. And that is the problem that complete linkage tries to address. And again, I have a visualization for this. This is this chaining phenomenon. What you see here is things are grouped together, and you have this cluster, and then this was added to this, and this was added to this. You get these staircase-like things, where you have a fairly large cluster, and then you have just a small point or a very small cluster and gets added to that. So basically, you have one cluster growing, 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 and the next cluster growing, 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 growing. It's not a balanced solution. It depends on your application whether you like that or not. I actually was happy with this because I have these neuron reconstructions, right? So then I tried to group across sections, and this would mean one neuron would basically grow, and then would start growing the other neuron. And that came in very handy. But if I do this with complete linkage, this structure looks more balanced, right? If you compare these two structures, here I have more the staircase pattern, and that's not so much the case here. So I get a more, over the hierarchy, I get a more balanced set of clusters in terms of size. So that is complete linkage. So why don't we use complete linkage just all the time? It's our application. And complete linkage has a problem with outliers. And this is illustrating this problem. What you see here, these are 4 data points and 1 data point. And the solution that is intuitive would be to group these 4 together and then do this as a single cluster, right? But because of this very small epsilon, so I said the dark arrows here are 2 epsilons, Actually, this guy is unnecessary. And the bright one here is 1 epsilon. So let's say you have these three grouped together, and you have this guy alone, and you try to determine where this point goes. You say it's kind of in the middle, right? It's in the middle. 4 is in the middle between 7 and 4, and between 1 and 4. The distance is 3 to both. But because this point here is 1 epsilon closer, and this point here is 2 epsilon closer, complete linkage is going to group those two. Whereas single linkage is going to look at the closest point, so it's going to compare this guy to this guy and to this guy. So it's going to come up with the solution where it groups this over to here. So single linkage is more robust towards outliers, but produces these chaining clusters. Complete linkage has this benefit of giving you more balanced clusters over the hierarchy, but it has problems with outliers. And that's the video segmentation I talked about. This is Matthias Lundmann and Irfan's Esser. It's from 2010. When it came out, the result, like I had a colleague who was working on video segmentation at that time, and he told me this is mind-blowing. Like, I don't think it's maybe that mind-blowing now, 5 years later, but this is really efficient and fast and produces good results.
We present a technique for segmenting videos of dynamic scenes like this one.
I don't understand that because I extra looked at this guy today.
We present a technique for segmenting videos of dynamic scenes like this one into perceptually distinct regions.
Mickey Mouse it is.
We present a technique for segmenting videos of dynamic scenes like this one into perceptually distinct regions. Applying image segmentation to each frame individually lacks temporal coherence and consistency of region borders over time. In contrast, our novel video segmentation algorithm treats the video as a 3D volume, initially obtaining a temporally coherent oversegmentation of spatial temporal regions. We then apply a novel hierarchical segmentation to merge regions into superregions based on appearance and motion information. The hierarchy is saved as a tree, allowing the granularity to be selected after segmentation. We now show some more segmentation results. The skin and wetsuit of the surfer are coherently segmented even when he jumps and turns. Our algorithm reliably segments dynamic objects such as the sea spray. The numbers on the shirts of the football players are preserved despite challenging partial occlusions. The actors are segmented as 3 independent spatial temporal regions. Fine details such as the top of the wave are tracked reliably.
So I cut the video here. So I don't know if everybody got that. What they're saying is they're doing this video as a 3D volume. What they're doing is they're applying hierarchical clustering to that whole volume, and they're saving the whole tree. And then they do exactly what I said. They're actually providing the user with a slider. And they can go back and forth between the video frames, and they can actually adjust the threshold. And what happens is, if the threshold is very small, you get a lot of this over-segmentation. So here were all these different small regions here. And then the more and more you go up in the hierarchy, you can actually see that you're starting to segment out the face, the hair kind of, and the upper body. And the segmentation, what was so cool about this method is the segmentation is pretty stable across time because they're looking at the whole volume. That's also a benefit. Hierarchical clustering is fast. Also fast in the beginning to compute. So and their software is actually online if you want to play around with it. So the Swiss roll problem, as I said in the beginning, the clustering people are very keen on doing spirals because k-means has this notion of looking for blobs in the patterns of the data, and spirals are not blobs. So that was always considered a challenging task for clustering papers. And scikit-learn allows you to specify a connectivity between points and to have this constraint that points that are grouped need to be adjacent. And that can solve you the Swiss roll problem. So this idea is, if you would unravel Swiss roll is because they have this delicious cake, right, that is in the spiral form rolled up. It's really nice. So the idea is to unravel the spiral, right, and look which points are adjacent on this manifold. And with connectivity constraints, you actually get the clusters along the spiral. Here, you can see it was, again, this case where it jumped across the gap. And this is something we actually would not like to see in a clustering solution. So by specifying these connectivity constraints, right, they got rid of this, and it can only group points that are adjacent on this manifold. But you have to specify the connectivity between points. So we've talked about all these clustering methods. Are there any questions about any of those? Because otherwise I'm going on to the evaluation of clusterings. Okay, cool. So evaluation criteria, that's hard. That's really hard. That's something you need to think about in unsupervised settings in general. Like, how do I know that the pattern I came up with is sensible? How do I know that my clustering solution actually made any sense? Sometimes you are in this case where just obtaining labels is very, very expensive or hard. And if you only have very, very few of them, it might be worth considering doing an unsupervised method and then using the labels only for evaluation. Then you at least have solved that problem. But then, so with that, you only can evaluate the structures you knew were there in the first place. So that only works if you're not looking for novelty. So how would you evaluate looking for novelty and whether that pattern that you found makes any sense? So one way to look at clusters, but that needs this notion of labels, is to compare points within a cluster. And you say, this is the Rand index, so you say 2 points that should have been in the same cluster and are in the same cluster. That is what I was looking for. So you say this is a true positive. And then 2 points who are in separate clusters and should have been in separate clusters are a true negative. And then you also have this notion of a false positive because they're in the same cluster, but they actually belong to 2 different classes. And you have the false negative where they are in different clusters. They actually should have been in the same one. And then you can compute this Rand index, which just divides your true positives and your true negatives by all the different connections. So what percentage did you get right in your clustering? But you see, there is this notion in this evaluation measure of having these points should have been in the same cluster in the first place. So you need labels to compute this. That's a drawback. So this is going to be brief, but I want you to have this notion because I thought this is one of the really, really cool solutions to evaluating clusterings. And I haven't seen it much out there being taught, but this was actually developed by a guy who worked in my PhD group. And I always thought this is really a good way to evaluate clusterings. Because you have this notion of stability. A good clustering solution, this is now about generalization. We said a good clustering solution, often you are looking for something that generalizes to the new unseen data. But if you don't want to do this knee-elbow visualization, or maybe that graph doesn't look as well, how do you know that your data will generalize well? Choose your K in a way that the pattern you found generalizes well to new data. And that is this notion of stability. So I have a clustering problem here. So the question is, I can say these are 2 clusters. Valid assumption. I can also say these are 3 clusters. And if I have just this, it's actually hard to say in this problem whether I should choose 3 or 2 clusters. Like, if I only look at the points in the beginning, maybe I would just have said 2, but if I have in my mind these could be 3, right, then grouping these 3 and these 3 actually is not that far-fetched. So what should be the solution here? So the idea is to split your data and to have a second set. And that whatever clustering you choose here should generalize well and also explain this data. because it's coming from the same source. And you can see if I would cluster this data here with 3 clusters, I would come up with a different solution, even independent of my different k initializations. Right? Because these points, if you tell me 3 clusters, I would group these together, these and this. And these centers really are different from those. Whereas if I do 2 classes, then the centers are somewhere here. And these centers would also explain this data. So that is this notion that a clustering should be stable. And in this case here, using k equals 2, gives me these 2 clusters that can explain both data sets. Whereas with k equals 3, I get a solution that explains one data set very well, but then has problems generalizing to the other data set. So that's all well about intuition, but how do I do this now? How do I evaluate this? So the idea is that you turn this into a supervised problem. So I'm taking the clustering here with k equals 2, and now I'm assigning labels. Note, these labels were not given to me. This is not a Y that we had before, where somebody would come to you and say, this is your data, this is the label, this is what it should be. What I'm doing here is I found that pattern. So I say, I find a clustering, and now I assign these points red, and I assign these points blue. I just made up a Y that is correspondent to the clustering solution I found. But now I have a supervised problem. Now I can train a classifier of my choice. Random forest, support vector machine, we've been there. So if that clustering was a good idea and is comparable to that clustering, now I can turn this also into a supervised set. And then I can use this classifier and compute the test error on the second set. And if the clustering is stable, that error should be small. Does that make sense? So the really cool idea here is to use the clustering to transform our unsupervised problem into a supervised one. And then to see whether that transformation, right, whether the labels assigned by our clustering solution were useful to generalize to the new data. Okay, I see you're getting tired. I know we covered a lot today, but that's actually everything I wanted to say about clustering. So we went over 3 different clustering methods. You all know now k-means clustering, where I shift my random initialized centers around. You know mean shift clustering, where I don't have to specify the number of clusters, but my window size, and I look where all the points converge to. And we've talked about hierarchical clustering, where you keep the whole tree and sometimes just want to define a threshold afterwards, and sometimes you just want the user to have the whole tree to identify structure. And we've talked about how to evaluate your clustering if you have labels or also if you don't. That was it. Have fun.